Hello, my name is Conchita Kamanzi and I'm a PhD student with the Minerals to Metals initiative based at the University of Cape Town.
The generation of dust in the mining environment is inevitable. Although there are suppression controls, they only minimize the problem and cannot prevent the entrainment of potentially toxic dusts into the ambient air. In the case of coal dust, historical links have been made between the dust itself and respiratory diseases contracted. In order to improve on the decision-making for future mitigation strategies in the mining environment, the harm attributed to inhalable dusts needs to be redefined in order to holistically represent risk. The aim of this project is to develop a risk characterization protocol for inhalable coal dust that takes into account the most influential physicochemical characteristics of coal dust towards inhalation toxicity. In this presentation, we will walk through the 3 pillars of our project plan, which will enable us to achieve this aim. Stage 1 looks at the characterization of the dust material. Here, a range of coal samples will be sized to an inhalable fraction which has the potential to become deeply entrained in your lower lung. These samples will then be analyzed using a quantitative imaging tool for mineral matter called the QEM-scan. This tool will allow us to mineralogically map our dust sample and obtain statistical data on a range of physical characteristics such as size, shape, mineral grades, liberation, and mineral association. The second stage looks at the measure of cellular response to the dust as a measure of harm. For this, the particle characteristics will be correlated with the cellular response in order to generate indicator variables for risk characterization. Specifically, we will be conducting in vitro tests on macrophage cells to measure the cell death rate and their potential to produce reactive oxygen species. From here, we will use a regression model to correlate the responses to the characteristics and obtain indicator variables which represent the most influential characteristics of dust which have the potential to induce a toxic response. To zoom into the process, a learning nonlinear multiple regression will be used to represent the percentage of relative importance or partial dependence by taking each branch of the regression and translating it into a proportion of a defined space. Stage 3 looks at the representation of harm using a weighting and scoring algorithm to define the risk characterization protocol. Within this protocol, there are 2 parts. Part A focuses on the indicator variables generated in Stage 2. These variables will be used in a weighting and scoring matrix which will outline the potential harm of the different coals. Part B of the protocol intends to outline the tools and methods used to individually analyze and characterize the dust particles. Returning back to the 3 pillars of the project, let's conclude with the expected outputs of each stage. Stage 1 will provide a defined method for the individual particle analysis of coal dust physicochemical characteristics. This will aid in the identification of potentially harmful dust being generated from the mines, ultimately providing information to guide in ensuring the safety for those who work and reside near mines. In Stage 2, the novel use of a learning nonlinear multiple regression to flag dust characteristics that may induce a toxic response has the potential to allow for a more cost-effective and ethical screening strategy for factors that may affect inhalation risk. The translation of indicator variables to measure relative risk of the different coal dusts in Stage 3 allows for the potential harm of coal dust to be ranked on variables inherent to the physicochemical properties of particles, enabling for a more holistic representation of risk.